Okay, so today I want to touch on a few things quickly. So first, homework number 1 is posted. So it's 3 problems, each of which has a couple of parts. There's some pencil and paper work, and then there's also some computing work. And the coding you can do, again, either in MATLAB or Python, if you want support, either from me or Nada RTA. If you're fine going without support, you can program in Julia or another language of your choice. But I would advise probably MATLAB is the one that will support the best, and then Python pretty close. So you're welcome to choose what you want to do there. So we will talk today, time permitting. If we get through the whole lecture, we'll cover the material for 2 of the 3 problems. So they'll be due not a week from today, but 8 days from today. So next week, Wednesday. And then there's a third problem that involves coding, and that really will draw content from Thursday's lecture. So you can get started on that one if you want to, but by Thursday, you'll have the material. Another point, the syllabus here, we updated to add office hours. So if you scroll down to the bottom of the syllabus, you can find my office hours here will be Thursdays from noon to 2. And Nada RTA, her office hours will be Mondays from 9 to 11 and Tuesdays from 11:30 to 1:30. And you can join office hours basically via Zoom, or you can come over to Herrick Laboratories, which is called H Lab on the Purdue map. That's kind of on the south west corner of campus. And so that's where both Nada and I have our offices. And then let's see, anything else? I think that's all for now. So today's lecture plan, I want to continue with the material that we didn't quite finish up from last week, Thursday's lecture, where we were talking about electricity markets and DERs and kind of some of the motivation for DERs. And then we'll jump into a third lecture here where the slides are up. We'll talk about linear ODEs, which turns out to be the modeling instrument that we use for most DERs. So any questions before we dig in? All right. So you may remember last lecture, we talked about regulation, and we talked about how there traditionally were vertically integrated utilities that owned both generation, transmission, and distribution assets. And it wasn't really until the turn of the century, roughly, that that structure started being disturbed a little bit. And first, it was kind of breaking up on the generation side to allow third-party power providers, something like a small hydro farm, to sell electricity into wholesale markets. And then the transmission system basically got separated from the generation and distribution systems. And so now transmission systems through most of the US and some of Canada are run by what are called transmission system operators, TSOs. And within that umbrella term, you have either ISOs, independent system operators, who typically operate in one state, or RTOs, regional transmission organizations, who would cover multiple states. And we talked about the different flavors. We're in the MISO Midwest region here. And then we talked about how these TSOs make decisions at varying timescales, kind of from fractions of a second all the way up to multiple years. And we zoomed in particular on this economic dispatch problem because it's, I think, quite relevant for some of the DER material that we'll talk about in this class. Okay, so we talked about that economic dispatch problem, and I guess at this point I'll slow down and kind of just revisit this material from scratch. So the basic form of this problem is that we want to minimize the overall cost to consumers of delivering electricity. And so one way that we do that is basically by soliciting offers of generation from a number of generators, or from resources more generally. They could be also, say, a battery that has a lot of energy stored and is willing to discharge to help people meet demand. So each of these blocks here represents an offer from a resource. So this is the amount of energy, is the horizontal width here. And then the height of these blocks are basically the price at which that amount of energy is offered. So here we have a small expensive generator or resource. Here we have a small cheap resource. And then here we have a big and kind of mid-price resource. So in reality, these problems are solved using numerical optimization methods that are very sophisticated, and they involve lots of constraints related to the architecture of the transmission system. Someone mentioned the other day about how not all power plants can turn on and off really quickly. So there might be constraints around, for example, a nuclear power plant having to run, something like that. But this is kind of a caricature. This merit order thing that I'm going to present is kind of a simplified caricature, but it provides a useful heuristic that's sort of directionally accurate for how these dispatch problems are solved. So the basic idea is we take these kind of random offers, we sort them in order of merit, where the lowest cost producer we define as the highest, sorry, the lowest price producer we define as the highest merit. So we go from low price all the way up to high price, and this is kind of at the bottom of the merit order here. And then we get demand forecasts. So this could be from utilities like Duke Energy in this area, or other utilities. We talked about ComEd in the Chicago area, and so on. And sorry, I just want to double check to make sure I'm sharing screen. Okay, I am. Good. Okay. Right, so we get demand forecasts, we add them all up, and that's basically the total amount of energy that we need to procure over, say, an hour. And then we asked basically, okay, if you have this demand forecast and you have this merit order, how do you decide who runs and who doesn't? And it's sort of the obvious answer is that we dispatch starting from the kind of highest merit generator, the lowest price merit, and then we kind of move to the right. And we stop once we have as much supply as we need to meet the demand. And the last generator dispatched is called the marginal resource. And we talked about, although there's different ways you could imagine paying the different generators that get dispatched. One way that's used kind of throughout the US markets, it historically was used in European markets, but this is changing, is basically what's called marginal pricing. So you look at the price associated with the marginal resource offer, and you say that price is the value of electricity right now. And then you pay everybody that same price, regardless of what their actual cost of producing power is. Okay. So that's, again, merit order. It's a useful heuristic. It's not exact. And I just want to show you one way that we can have deviations from the merit order. And this is kind of relevant for some of the work that we do in DERs. So this has to do with transmission constraints. So, a power line can only carry so much power over it at any given time, and what are called load pockets. A load pocket is just an area that typically has high electricity demand, but for which transmission into that area is often constrained. So there aren't a lot of power lines going in. So New York City is one great example of this. Also, much of the whole Northeast, kind of the Boston and surrounding area is another example, where you have high demand, not a lot of power lines going in, and so you often get into this transmission constrained situation. So the idea here is we have a total demand D. This could be, hundreds of megawatts or even gigawatts. And within the load pocket, there may be some power plants or some batteries or a collection of DERs, for example. And we also have a power line coming in. In this very simple example, there's only one power line. In reality, there would be more. And then outside of the load pocket, far away, we might have some more inexpensive resources. So this could be a far away coal power plant, for example. Okay, and this line is constrained to a capacity C, and that is below the demand that we see in the load pocket. So what we would like to be able to do is take the whole demand D and meet it all from the inexpensive resources that's out of town. But in reality, what we have to do is basically we can only take up to C from this generator. So we dispatch an amount C of energy from the low-cost generator, and then the remainder here, D minus C, we get from the more expensive generator or resource that's inside of the load pocket. So we get D minus C here, we get C over here, and we get a high clearing price, even though this generator out of town is cheap and has plenty of capacity. So we could take this whole green rectangle that gets dispatched from the expensive resource, we could put it down here, and the low-cost generator could produce all of that power. But unfortunately, due to transmission constraints, they're not able to. Yes?
So is that why the Wade utility plant is right near campus? Because otherwise you would have to send all that power in on just a few lines?
So the question is this why Purdue has its own Wade utility plant here on campus? I would say that's one reason. Another reason is we do what's called combined heat and power here. So we have natural gas generators on site, which generate electricity, but also basically, as you know from thermo last semester, yeah, exactly. Steam comes out and that's used. Basically, that's what's heating the building that we're in right now. So if you look at the efficiency overall of a power plant that produces both heat and power, typically it's much higher than what you would get. And therefore, it's much lower cost to do it that way. So yeah, these are related, but there are other issues as well. Okay, so if you think about this, this is one reason why you might see an entity oppose a political process that allows more transmission to be built. So they might say, I don't really want to build new power lines coming into this load pocket. Even though for the people living in here, it would be great, right? They get lower cost power if they're able to get it all from this inexpensive resource. But because of this line constraint, they pay a higher cost because they're pulling power from this guy, right? But suppose you owned this resource here, you own this power plant. Then you don't want transmission to be built because if it does, you're basically out of business, right? Very, very rarely will you actually be called on to produce power. So this owner probably doesn't want transmission, but also this owner probably doesn't want transmission, right? Because it would be valuable for them to be able to get more power into the city. However, if this guy was knocked off of the margin, right, if they stop being the marginal generator, then the price of electricity would drop significantly, in this example by like 80%. And yes, this generator would produce twice as much power, but they would get paid 20% of the price, and so they would lose out overall. And then often what happens is you have the same generation company might own the inexpensive resource out of town and the expensive resource in town, right? And in that case, you have very strong incentives. And actually, you can get into market manipulation issues, which can happen. These ISOs are nonprofits that actually have staff whose job it is to try to watch what people are doing in the market and detect essentially bad behavior, trying to manipulate the market. And so one way you can imagine, probably you can imagine other ways than this one that I'm going to talk about, but one way potentially that I could manipulate the market if I own both of these resources is I could submit a very high, so a very tall rectangle here, a very high price offer, but only a little bit of power, and just trust that I'm going to be needed to turn on at some point, right? So I will set the clearing price over here, and then I know that my other power plant outside of town is going to produce almost all of the power and get paid a very high price for that, right? So the amounts of money involved in market manipulations like this are not small. They can often be counted in the millions or even the billions of dollars. So just because we use so much electricity, right? And so the overall size of these markets is vast. So if you can, do a manipulation that gets you 1% of the total market value, you can make a lot of money. All right, so there's other examples, and I'm not trying to say that everybody playing in these markets is very devious and trying to manipulate things, just that there are opportunities for that, and so it's an important job at TSOs basically is to watch for stuff like that. Okay, so with all that in mind, I wanted to get into just a couple of quick examples of why we might be interested in doing DERs, right? So if we were building a power system from scratch, why might we try to build a more distributed system than the one that we have today? So here, this is an illustration of kind of the central grid that we have today. We have large centralized resources. We have demand over here that might have a peak load L measured in watts or gigawatts or whatever. And then in between, we have the transmission system and we have the distribution system. Each of those involve, transmitting power over conductors that have some non-zero resistance. And so we get energy losses there. So we have an efficiency that's less than 1 for transmission and for distribution. And so the amount of power that has to flow through the lines here to get this peak load L delivered, we need an L divided by eta, the efficiency of distribution, going into the distribution wires. And then we have the product of the efficiencies in the numerator or the denominator here for the amount that has to come out of the generator and go into the transmission system. So the product of these efficiencies might be 90 to 95%, somewhere in there. So we're only increasing the total energy flow by 5 or 10% probably, but that's not insignificant, again, when you're talking about sort of billions of dollars. But the blackout risks associated with this system, basically if any of the blocks here in this chain of resources fails, then the entire system more or less fails, right? So here, if we imagine having only one generator, if they go offline, this person has a power outage. But also if the transmission or the distribution lines drop, this person over here has a power outage. Okay, and then we can talk about how much it would cost to build this system to meet peak demand L over here. We would need basically a cost of generation, right? This would be our price. Pi here means price, and CR means centralized resource. So we have that price basically multiplied by the power that would flow through that resource. And we do the same thing for the transmission and distribution blocks. We add all that up and do a little bit of algebra, factor out the L over eta D. And this is what we get for the overall cost of building out this system. So today you can get generation, say solar, for about $1 a watt. So this would be maybe 1 for the pi CR. Transmission might be that same order of magnitude, maybe a bit lower. And distribution might be, again, something like $1 a watt. So this overall thing here might be around 3, and we get basically 3 times L. Okay, and then here is not the sort of DER example, but kind of the other extreme is a totally decentralized system where you have no network, just everybody kind of does their own thing. Everyone is an island. So here, this distributed resource could be, for example, a diesel generator, or it could be a solar plus battery system or something like that. And here, it just directly serves load. There's no efficiency losses. There's no need for other infrastructure dependencies. And so the blackout risk is just basically that this one distributed resource goes down. So lower risk as long as this resource is reliable, which it may or may not be. And then we can run the cost of this thing, which is just basically the price pi dr of this distributed resource times the peak demand that it has to meet. So that is lower than the central cost that we derived on the previous slide, provided this condition is met. Basically, we have an L here, and we had an L here, and so those L's cancel in the inequality, and we get a condition that relates only to the prices and the efficiencies. And so this says as long as the price of this distributed resource is below this function here, which is the stuff that was multiplying L in the other equation, as long as pi dr is below that, which might be about $3 per watt, then this distributed system both has potentially lower blackout risks, but also lower capital costs to build than the centralized system. Okay. Now, I'm not giving, these aren't necessarily, I'm just using round numbers here for the numerical example. These can be quite different. So for example, the price per watt for building a nuclear power plant might be not $1 per watt, but like $15 to $20 per watt. So it can be significantly higher. Yes.
Looking back to the last page.
Yes.
Notice that you use the same fraction for the central resource of generation and transmission. If we had if we were starting from the base fuel, say like the oil or whatever, would we have like an efficiency of generation in there as well? Like, why are those two the same?
So here we have the same L divided by A to T, A to D. We have that applying to both the, say, generator and the transmission system. Would there not be an efficiency associated with the central resource? Yeah, so we could draw another arrow coming in here that would be like the fuel input to this central resource. And then there would be a conversion efficiency, say, from gas out here to electricity on this side. And that efficiency would certainly be relevant for things like the cost of producing energy. But here, there's kind of a difference in this example between energy and capacity. So here, capacity means basically your ability to meet peak power demand. Whereas energy would be like over the course of a day or a month or a year, can you produce enough integrated power, right? Enough energy over time to meet demand. Does that make sense? So the electrical output from this resource has to basically be equal to the electrical input for the transmission system. And that's why the coefficients there are the same. Yeah, but good question. Thank you. And of course, people, if anybody else has questions, please feel free to ask. Okay, so then the distributed system is kind of a middle ground between these two. And you could argue that it has kind of the best of both worlds. So here we have the full grid as it exists today with big centralized resources, high voltage transmission, medium voltage distribution, and we have our same peak load L here. But now we imagine also having a distributed resource. Again, this could be a diesel generator, it could be a fuel cell, it could be a solar plus storage system, something like that. And it can contribute an amount G to meeting the peak demand L here. So by doing so, it alleviates the burden that this peak load here would place on the centralized grid. So rather than needing L here, the full peak demand, we only need L minus G, some intermediate peak demand. Okay, so in this system, it has more redundancy, right? So the blackout risk is only when both the distributed resource and something on the grid fails. So the reason here is if we only have a failure on the bulk grid, well, then we can flip to backup power. And this is the whole reason people buy backup generators. And we'll still be okay. We'll still be able to keep the lights on, keep medicines cold and things like that. Conversely, if this distributed resource fails, well, we're still fine as long as the grid is operating, right? So it's only really when we have the intersection of those two events, a failure both of the backup local and of the bulk grid, that we end up with a blackout of the load. So higher resilience. And it turns out that we have the same condition as for the off-grid system. for having lower capacity cost. So the condition there, again, so we can write down the cost of this system, and this is the full cost of the centralized system. And you can do some math here. It's not particularly challenging, a little bit of algebra, and we derive the same condition that we had from the previous slide. So you can see there's an L here multiplying the same coefficient that we have on the right-hand side. So that L term is going to cancel on the left and the right. And then you can see how the G will cancel out because it's left kind of in both of the remaining terms over here. Okay, so that ends up being the same condition. So, maybe you have $2 a watt here for a solar plus storage system, or even $3 a watt. But if it's below the kind of combined capacity cost of all this centralized infrastructure, then it may still be cheaper and more resilient to build that system. Yes, question.
In this case, if on the distributed resources, does it necessarily be stored in some place, and then when the line breaks, interline breaks, and that stored energy would come into the picture? So if that is the case, whether there will be any efficiency loss and energy loss.
Okay, so the question, as I understand it, and correct me if I misunderstood, is suppose that something fails out here on the grid. Then we have this line connecting the distributed resource to the load. And the idea is that this thing turns on and then begins to meet load. And your question was, is there an energy loss associated with that?
Energy storage system over there that because the distributed resource usually would be something like a solar power system.
Right.
Right. So whether it be stored there in some place and then it's distributed when the line is failing.
Yeah, so the question is, when something fails on the big grid, is there energy storage or something like that associated with this distributed resource in order to help it still continue to meet the load, right? And the answer is typically yes, but not always. So if you have a backup diesel generator, it typically won't, it has a bunch of chemical potential energy stored in the fuel, right? But it doesn't have, for example, a big battery at least. A solar system, like if a blackout happens during the day when the solar panels are producing power, typically they will have inverters. And if those inverters have the intelligence to be able to, continue to supply power to the load in an islanded fashion, right, separated from the bulk power grid, then in theory, the solar could meet load directly by itself. More often, what happens in off-grid solar systems is that you couple them with batteries, and then the combination of solar and batteries would meet demand. Yeah. Yes.
So to add in the distributed resources, is it more of a, would you need to make changes and adaptations to the grid or to your own house or your own community or whatever?
So the question for folks online is, if we were to add in a distributed resource, do we need to make changes out here to the bulk grid, or is it sort of only local changes that need to happen? And the question, I guess, as with most things, the answer to that is it's complicated. I would say more it involves changes at the building or the community level, right? So to put a solar plus battery system on a house, if you happen to own a house, you would need to pull permits probably from the municipality. If you wanted the ability to push energy back out into the power grid, you would need approvals from the local utility, right? And so the utility, again, is out here on the grid. And so there is some interaction between what you're doing locally and this kind of more global system. And then, of course, there would need to be work done. You'd have to get up on the roof and install stuff and do wiring and things like that. And that might require changes, but only local, kind of within the building. And then, of course, if a lot of people did this, like if the whole town of West Lafayette put in solar and battery systems, then we would buy much less energy from the bulk grid. And so that would have kind of knock-on effects that propagated out potentially to the MISO transmission system and out to the generators who would normally have been producing energy and selling it to us, right? So I think there can be indirect effects that propagate. That's a good question. Thank you. Okay, so just to summarize, so this is a very highly simplistic analysis, right? And in reality, power grids are huge and complex, and so these analyses get much more complicated. But the basic idea that we've laid out here, the basic motivations for why we might want to do DERs remain. And those are two. We think we can improve resilience. So when something like a wildfire takes out part of a grid, or when severe winds or a severe storm knock out a power line, something like that, it can be valuable and even life-saving to have local power or generation. And also we can reduce the cost basically. So we don't have to build out as much poles and wires and transformers and all that stuff if we have local generation. And then on top of that, you may or may not think this is interesting or useful, but ERs, typically because they don't require as much approval from as many organizations as building big resources, typically we can deploy them faster. So just as an example, a nuclear power plant might take on the order of 15 years and maybe $20 billion, somewhere in that range, to build. So great, clean, et cetera, has its own set of risks, but mainly if we want to address challenges related to pollution, climate change, et cetera, quickly, then there's value to being able to be sort of agile. And then we also talked about how some 5 to 10% of the global economy is energy sales. And that's just a huge mechanism for sort of taking money from everyone and concentrating it into the hands of the relatively small number of people who are major shareholders in big energy companies. And so maybe you care about that, maybe you don't. But if you do, you might see some value in shifting basically production of energy so that it's more in the hands of people so that you have less of this kind of concentration of wealth and power. Okay, again, maybe you care about that, maybe you don't. You can draw your own conclusions there. But so these are some basic arguments for why we might care about DERs. So now this is material I meant to present last week. I'm going to switch to today's actual lecture. We're out of time and I'm going to need to adjust at some point. But any questions on this material before we kind of shift gears and start talking about math? Yes. Can we not talk about math? That is a good question. And the answer is it's complicated. Again, it really depends. No, we got to do it. It's going to be 2 lectures of significant math, and then we're going to move back into DER land. And I'll try to give DER examples as we go. So. One of my PDF viewers kept my face on there. The other one did not. Not sure what's going on there. But okay, so today, the kind of lecture that I meant to get to on the schedule, I guess it's not great that it's only lecture 3 and I'm already behind, but that's okay. There's some squish on the schedule. We'll adjust. But so yeah, we're going to go back to basics and talk about linear ordinary differential equations, which you should have seen at some point in your undergraduate training. And it's okay if you've forgotten those completely. Again, we're only talking about maybe like 10% of what you would learn in ordinary differential equations class. So all the nonlinear stuff we're not going to talk about. We're not going to talk about partial differential equations, which involve multiple variables. It's all going to be single variable stuff. So for some of you, this will be very boring. For others, it will be maybe a little scary, but hopefully not too bad. So we'll start by just getting kind of consistency of notation for the kind of math that we're going to talk about in this class. And then we'll talk about first order linear scalar ODEs, kind of the simplest type of ordinary differential equation. We'll talk about a battery example, which can be modeled in this very simple way. And then we will move on to talk about what are called vector linear ODEs. So here you would have multiple variables, but all kind of in a linear fashion. I'll talk about how that works. Okay, let me just try to take the temperature of the room here. So how many people are like, ODEs is super easy, I'm very comfortable with it? Like you probably just took the class last semester, right? Yeah. Okay. Okay, and how many are like, oh, I hate this. I'm worried. I'm a little nervous. Nobody, and everyone else is kind of in the middle. Okay, so that's good. I guess that's where I want you guys to be. All right. So a scalar just means a number. Okay, starting from the very basics here. Just so this is just a number, 1 or pi or 2.7 or -3. This thing R with a bold on it, we denote as the set of real scalars or real numbers. And real there means kind of something different, but it's not integers, so just 1, 2, and 3. It's not rationals, right? Ratios of integers. It's not imaginary numbers. It's not complex numbers. It's only real numbers. So you can think of this roughly as sort of decimals, but it can be an infinite number of decimals. And then the notation, alpha is a scalar. So this means alpha is an element of the set of real numbers, real scalars. So that basically just means that alpha is a real scalar. So we'll use notation like this mainly to sort of denote the dimensions of things, because we'll be talking about scalars and vectors and matrices. Okay, a vector then, at least for our purposes, is just an ordered list of numbers. So you have a bunch of scalars, you put them in a stack them, and that's a vector. The dimension of the vector is just how many entries are in it, so it's the length of the list. And then, we differentiate column vectors, so vertical stacks of vectors, from row vectors, horizontal ones. And again, just like we denoted the set of real scalars by R, here we use Rn, so the power n, to denote n-dimensional column vectors whose entries are real scalars. And then if you pick some element here, so some n-dimensional vector, this will denote a column vector specifically. So unless we say otherwise, every vector that we work with is going to be a column vector. So we write that either with square brackets as a1 through an, where ai here is the element number I of the vector a, or we will write it kind of like you'd use for a point, right? So point x comma y we'd use with rounded parentheses here. So even though it's written horizontally, this does not indicate a row vector. You should note that this is a column vector. And then matrices, just like a vector is just a list of scalars, a matrix you can think of as a list of vectors. So it's a rectangular array of numbers, and the size is the number of rows by the number of columns. And by R, m by n, we denote the set of m by n matrices, so m rows and n columns, that have all real entries. So you can imagine dealing with complex matrices where you have both a real part and an imaginary part, but we're not going to deal with those in this class. And then again, an element of Rm by n, well, that's just an m by n matrix. And we'll use notation like this mainly to denote the size of things, the dimensions of things. So we write that out in these square braces. So a11 through a1n, this is the first row of A, and then all the way down to the bottom row here, starting with row m, am1 through amn. And then the entry ij, or the element ij, we denote basically this is just a number here, and we denote it with capital A with the subscripts ij. Okay, and then the transpose of a matrix, basically you just take every row of the matrix and you write it as a column. So we take this row a11 through a1n and we write it vertically rather than horizontally. Okay, and so there's just a general idea that a matrix is a generalization of a vector, and a vector is a generalization of a scalar. So if you like, you could write a one-dimensional vector A. Well, that's just an element of R, or R1 here. It's just a scalar. And n by 1 matrix is just a column vector, an element of Rn. So for those reasons, we write n by 1, we drop the by 1 and just write that as Rn. And then R1, we drop the 1 as well and just write it as R. Okay. Any questions about this so far? I feel like should be pretty basic review for everyone. Okay, good. All right, so a couple of operations that we'll deal with. One is scalar multiplication. So if we have a scalar and a vector, those commute, meaning alpha times a, the scalar times the vector, is the same as a times alpha. And the same is true with a scalar and a matrix. So these are very simple, exactly what you would expect. And then we have vector by vector multiplication, and there are various interpretations of this. There's what's called the inner product and the outer product. But we're not going to talk really about outer products at all in this class, only inner. So for two vectors, A and B, both elements of Rn, meaning both n-dimensional column vectors, the inner product we write as A transpose times B. So A transpose for a vector A, a column vector A, just means writing it as a row vector. So we have the row vector here, A1 through AN, times the column vector B1 through Bn. And that ends up just being the, basically take the element-wise products and add all those up. And that's what we call the inner product. You might have called it a dot product in a multivariable calculus class, sometimes denoted A dot B, or in a physics setting, they use what they call bra and ket notation. So you may have seen that before, but it basically means the same. All right, so just as an example, sometimes we may use this. If you define this thing 1 as a vector in Rn of all ones, so bold 1 just means a vector of ones. If you take the inner product of a vector of ones with any vector, you just get the sum of the elements in the vector. Okay, and then we can also have various notions of multiplication for vectors and matrices. So for an m by n matrix A and an n-dimensional column vector B, we define AB as this thing here. And we can interpret that in multiple ways. One of them is just you take every row of A and you take the dot product or the inner product with the vector B. And then you store that basically in, take the first row, multiply by B, and store it in the first element of the vector AB. And you go all the way down to the bottom row. So you can think of matrix vector product as just a list of inner products. Another way to think of the product AB is basically noting that this whole thing here, all the coefficients, form basically the first column of A, which we can think of as a vector. So we have B1 times that column, shows up down here. And we do the same thing here all the way out to the sort of right-hand column. We have Bn multiplying the whole column of A there. So you can think of this thing AB as a mixture or a linear combination of the columns of the matrix A, where the weights in that linear combination are the entries of B. So as an example, if we take the identity matrix, which is just a diagonal matrix with ones down the main diagonal, multiply that by any vector B, we get back the same vector. Okay, and then we can also define matrix multiplication. So here we have an A, which is an m by n matrix, a B, which is n by p. And I've noted here that the inner dimension, sort of the first dimension of B, has to be the same as the second dimension of A. So number of columns in A has to be the same as the number of rows in B. So multiply A times B. Well, that can be written as just the inner product, row I of A times row B, or sorry, row J of column J of B. And we store that in the element ij of this product matrix. So it's very easy to kind of get confused with matrix multiplication. Dimensions matter a lot. So the syntax here, AB, only makes sense. It only parses if the number of columns here, n, in A is the same as the number of rows in B. So it's important always to be careful of that. Whether you're writing code or doing math, you want to check that. And then we talked about this notion of commuting, right? How if you had a scalar and a vector, it doesn't matter if you have alpha A or A alpha, it's kind of the same, and the notation works either way. But when you have matrix multiplication in general, they don't commute. So you can't switch the order of multiplication. So first of all, the syntax AB equal BA, that only parses if A and B are both square. So if one of them is wide or tall, then the syntax here just doesn't work. And then even if they are of the appropriate dimensions, they're both square and n by n, this AB equals BA only happens for very special matrices. So in general, it's not true. And you can test that in MATLAB or Python if you want. Okay. And then there's lots of theory around inversion. We won't get deep into it, but if A is invertible, and this, at least for our purposes, we will only use inverse when talking about square matrices. But if that's true, then A and its inverse commute. So A inverse A is the same as A inverse. And either of them will give the product that's just the identity matrix. So you can think of an inverse as just generalizing kind of 1 over A, if A is a scalar. So if you take 1 over A times A, well, you get back 1. And the identity matrix is kind of a generalization of 1. All right, and then we will talk a little bit about matrix valued functions of scalars. So here, the notation A maps from R to R m by n means that this function A, it takes one scalar, one number as an input, and it produces an m by n matrix as an output. And we write it basically as just the entries, A, I, J of the matrix, and then we put a time argument or a t argument after each of those. So A of t, this is an object. It's just a list of numbers, an array of numbers, and it's the value of the function A evaluated at the argument t. And then each of these elements we think of as a function from real numbers to real numbers. So they take a number as an input, produce a number, a scalar number as an output. Okay, and then we can define some calculus operations on these matrix valued functions. So the derivative of this function A is exactly what you'd expect. It's just the list of derivatives of all the entries, all the entry functions. And we have a product rule. This will show up in a derivation in these lecture notes, which also will be in the homework. So if you have the product of a matrix AB, a matrix valued function A and a vector valued function B, the derivative of that product, it's kind of like the product rule from calculus. The same, we just have A times derivative of B plus derivative of A times B. Integrals, we can define the same way, just integrate element-wise. So nothing fancy there. And then the fundamental theorem of calculus, we also will use. So under some assumptions, basically smoothness of A, differentiability of A, we get that if you integrate the derivative of A, again, this is a matrix valued thing, but if you take the derivative element by element, and then you do the integral element by element again, evaluated from T1 to T2, well, that whole thing ends up just being the function A evaluated at T2 minus A at T1. So this looks just like the fundamental theorem of calculus in this integral form for scalars, but it's useful in again, a derivation that we'll do today. And then last, I don't think we'll actually get to this content today, but we will sometimes talk about block matrices, where each element or entry in a matrix in this representation is itself another matrix. So this can be useful when you're programming things to be able to store stuff as kind of blocks, matrices made of matrices. And it's important to have consistent dimensions here. So basically the row dimension of B and C have to be the same. The row dimensions of D and E have to be the same. And then the column dimensions of B and D and C and E have to match as well. Yes?
Yes or no on this, but I don't be off track,
Mhm.
but would that be the same as a third or fourth degree matrix? Or
Is this the same as a third or fourth degree matrix or tensor? No. So they're like a third order matrix or tensor would have another dimension, basically. So rather than just having rows and columns, it might have another dimension that goes back like this. But we won't use those in this case. Okay, so with that notation under our belt, we can talk about first order linear scalar ODEs. So a scalar ODE is just an equation that has a scalar valued function of scalars. So something that takes scalars as inputs, produces more scalars as outputs. That is the variable. Yes.
For the matrices,
Yeah.
So it's good to save all the data we have in a big matrix and then take some columns for specific parts we want to run iterations and stuff.
Yes. So for some programming tasks, it can be valuable to form a big matrix where each chunk of it is storing a particular type of data, something like this. Yeah. It can also be theoretic when you're doing kind of derivations and stuff. It can be a useful trick to be able to pack things into big matrices. Okay. Right, so we have a scalar valued function produces, it takes scalars as inputs, produces scalars as at outputs. And the thing about an ODE is that it has derivatives in the equation. And these are ordinary derivatives, so single variable derivatives rather than partial derivatives where you would have a multivariable function. So some examples here. You can have higher order derivatives. These are all ordinary differential equations, even if they have a third derivative, second derivative, something like that in them. And so solving an ODE basically means finding the function x that is the variable in these equations. All right, so we can categorize ODEs, and there's various ways to do this, but for our purposes, we pretty much care about two. One is the order of the ODE, which is just the highest derivative that the ODE contains. And the other is whether it's linear or not, linear or nonlinear. And a linear ODE is one that you can write in this particular special form, where you basically have a mixture or a linear combination of a bunch of derivatives of the function. And they're all weighted potentially by time varying or functions here. And each of the weights here is itself a function, but it's not a variable function. It's some input data that we're given. So these could be sines and cosines and exponentials and polynomials and stuff like that. Okay, so let's do a quick categorization here. So this one, what is the order of this equation? Yeah, so it's an order one, first order. And is this linear or nonlinear with the kind of exponential times x product? Who thinks linear? Who thinks nonlinear? Yeah, I was trying to trick you and you didn't get tricked. Good job. This is linear. So even if you have a weird function of t, the independent variable, the thing that defines linearity is whether you have sort of products of x or weird functions of x. So how about this one here? What's the order of the second one? Second order, right? We have a second order derivative. And is this linear or nonlinear? Nonlinear. And that's because we have a function sine, a nonlinear function of the variable x there. And then how about this one? So it's going to be third order. And is this linear or nonlinear? Linear, exactly. So each of these terms, the derivatives of the function, they show up only multiplying functions of t, not multiplying other functions or derivatives of x. So this one is third order linear. Yeah.
For example, x to the power of 2 is really nonlinear.
Yeah, so if we had up here an x to the power of 2 and x squared, then yes, this would be a nonlinear ODE in the same way that having a sine of x here. Seems benign. It's easy to create a nonlinear ODE, but we have really, really good, powerful solution techniques for linear ODEs. And for nonlinear ODEs, one of the sort of dirty secrets of the math department is that very few of them can we actually solve analytically. We can solve them numerically, as in you can program an algorithm that will, for given input data, given values of these functions or whatever, it can produce a very accurate solution. But we usually can't write down, with squares and sines and exponentials, we can't write down the analytical solution. Yeah, we can use Taylor series approximations. We can use numerical methods like, a Runge-Kutta solver for ODE. Who knows what that is? Yeah, that's fine. We don't need it. But, okay, cool. So yes, so now that was categorizing ODEs. What is an ODE? Let's talk about specifically first order linear ODEs and what are called initial value problems, or IVPs. So the idea here for an initial value problem is we have the initial kind of value of the function. So you could think of this x as being the position of something, and t initial could be times 0 when we start observing the object that's whirling around. And then we're given an equation that has basically, it's linear and it only has a first derivative showing up in the ODE. So this is kind of the simplest version of a differential equation that you can write down. Okay, and I'm going to walk through the solution process, and it's worth, I think, paying attention to this because we will get to what are called first order linear vector ODEs in a little bit. And one of the homework problems is going to be basically to repeat the steps of this derivation, but in the matrix vector case rather than the scalar case that I'm showing here. So the steps will be the same, but you'll now be multiplying matrices and vectors using the chain or the product rule rather for matrices and vectors and things like that. So you'll have to kind of keep your hat on and pay attention to dimensions of things. Okay, so we start out here looking at this ODE by multiplying both the right-hand side and the left-hand side of this over here by some function g, which we assume is positive, meaning for any value of its input variable, it always gives a positive number as its output variable. So we do that, we get a g over here and a g on each of these terms. And then let's move the ax over to the left-hand side. Okay, so nothing really done so far. And then we just are going to remember the product rule for scalar valued functions, right? So the derivative of f times g is f prime g plus fg prime, right? So that's all we're writing down here. And then we're just going to notice that this thing has an x prime g product, which is the same thing that shows up here. And it has a term here highlighted in blue that if we choose an appropriate value of g is going to be the same here. So what we'd like to do is take the whole left-hand side of the second equation and replace it by the left-hand side of this third equation. So that's the sort of the insight here. Whoever came up with that was very brilliant, but we're just kind of piggybacking on that idea. So as long as this dg by dt, the thing that multiplies x in the third equation, as long as that's the same as the ag, actually negative ag that shows up multiplying x up here, as long as that holds, then we're good. And we can replace the whole left-hand side up here with basically the derivative of x times g. Okay, so now we have to understand what kind of function g would satisfy this relationship here. So that is the question. So what g that always gives a positive value, we need that. And we need it to satisfy this kind of derivative condition up here. Okay, so let's denote any antiderivative of the function a, the thing that's multiplying g up here. Call that just the integral of a dt. So this whole thing is going to be a function of t in general. And there could be various antiderivatives that could have different coefficients. So if you integrate cosine, for example, you get sine plus c. And you can just choose any value of c, and the derivation will work. And for simplicity, you can just take that constant of integration and say that it's equal to 0. Okay. So if we guess a function g of this form, well, it satisfies the positivity requirement because e to any number, even if it's a really big negative number or big positive number, the exponential is always positive. So we satisfy that. And then we can check that it satisfies this derivative condition that we're looking for. So we take the derivative of g. We have an expression for g, so that's the derivative of this exponential thing. Well, to differentiate e to the f of x, you just kind of copy down the function, and then you take the derivative of the inside stuff. That's the chain rule. So then we differentiate this thing. Well, now we're taking the derivative of the integral, and that ends up basically just giving back the function. This is the fundamental theorem of calculus. And then we just observe that this thing here is g, and this thing here is negative a. So again, clever to sort of just come up with a function of this form. I'm not asking you guys to come up with that out of nowhere, just to show that it kind of meets the criteria that we need here from this function. Okay. So then now we're in a position where we can basically write down the solution here. So we know the g. We've got this thing here, dx g, and on the right-hand side, we have the product gb. Now we take integrals, of both sides, integrate from some initial time t initial that we're given to an arbitrary time t. Here, tau just becomes a dummy variable. So we're integrating with respect to t, and I didn't want the same variable kind of under the integrand as the variable of integration. So we change that to tau, integrate d tau. And then on the right-hand side, we just integrate this thing. So if you have an equation that's true, you can integrate both sides of the equation, and that remains true. So not much happening here, but now we can use the fundamental theorem of calculus to write this integral of the derivative as basically the delta of the function. So we have the integrand here, xg, evaluated at the final time t, and we subtract the same thing, xg, evaluated at the initial time. And then we haven't done anything on the right-hand side here. But now we have x basically almost by itself. So we just do a little bit of algebra, and we can isolate x of t, and then we've got basically the solution to our differential equation. So we add the xg product over, divide through by g. And this, by the way, is why we needed g to be positive, is because we wanted to be able to divide by it here and not have to worry about dividing by 0. And so this basically is our general solution for any values of any of the coefficients that we are given. We can just plug it into this formula, and we get the solution to our first order linear ODE. By the way, there are other ways of coming up with this solution, other kind of derivations that you can do. And I chose this way because this is the same way that works well for the vector case, which again will be a homework problem this week. Okay, so to summarize, the general form of our first order linear IVP, initial value problem, we're given the initial state, and we're given the governing equation here. And then this is our general solution, and we know what g is. Basically, look at this function a, take any antiderivative, and do e to the negative that, and that gives you the function g. So the first homework problem from this week, I think, will be fairly easy. It basically is just taking a concrete example of this first order linear scalar ODE. I give you the function a is 2 over t. I give you this function b here, and I give you the initial condition and the initial time. And basically, you just follow the steps and plug in everything to the appropriate places in the formula, and you should get the answer to this. By the way, you can take this and plug it into like Wolfram Alpha or probably ChatGPT or something, and you'll get, I'm sure, a correct answer. So yeah. But it's just the exercise is making sure that you understand kind of what each of the terms in the equations means. All right, so that's with kind of the general case where you had time varying coefficients for both the a and the b. We can specialize the results somewhat. So if that thing that multiplies x in the differential equation, if this thing is not a variable, not a function of time, but is in fact a constant, then the solution simplifies. Then G is just e to the negative ta. If a is a constant, you take its integral with respect to time and you get at. So e to the negative integral of a dt is just e to the negative at. So then our function here also we can simplify. So we know what G is. We can plug in that value here, and actually even over here. And we get this kind of simplified version of the solution. And very often that A is constant. So very often this is the form that we need. And then if B is constant and A is non-zero, we get an even simpler looking form. So now you can evaluate this integral. If B is just a constant, it factors out, and then you're just integrating e to the negative ta. You run the numbers there and you get this function. And actually, when we model batteries, typically B will be constant and A will be constant, and this ends up being the formula that we use for batteries. And then just as a kind of a sanity check, if A is equal to 0, so our equation is just, sorry, if A is 0 and B is constant, so our equation is just dx dt. You think of x as position, so velocity is equal to a constant. Then the solution to that should just be linear motion, right? Constant velocity means position increases linearly. And in fact, if we take our complicated formula, we parse all the terms correctly in this very special case, we get that the answer is basically just linear motion. And so that's what we expect. So this is kind of building confidence that the formulas we wrote down are reasonable. Okay, so I think we'll go through this battery example and we'll leave the vector case to Thursday's lecture, which again, you'll still have about a week after you catch that material. You have about a week until the homework assignment is due. And you'll have full set of office hours next week. Okay, so a very simple model of a battery here has the state, sort of the variable in the equation is the chemical potential energy that's stored in the battery. So battery is basically a device that converts electrical energy to chemical potential energy and then back to produce electricity, right? So here we say the time derivative of the stored energy is equal to the negative of the stored energy divided by tau, where tau is called a time constant. And this really has to do with what's called self-dissipation of the battery. So as you know, if you leave a device unplugged for a month, you'll come back, and even if it was fully charged, it'll only have some fraction of charge left, or it might not have any left at all, right? So this is to capture the fact that energy basically dissipates over time from storage. And then here, Pchem is what's called the chemical charging power. So this is by contrast to the electrical charging power. When you go from electrical to chemical, there's typically a conversion efficiency loss. And then if this term here, Pchem, is negative, that just means you're discharging the battery, taking energy out. So in this case, the battery, it ends up being a first order linear ODE, and A, the coefficient multiplying X, is a constant in this case, so we can use one of the simplified formulas. And then the thing B, the kind of additive term in that linear equation, is just the charging power. And so we can plug those things in and we get an equation for X of t, basically as a function of the boundary conditions there. And this is assuming that Pchem is constant over some time period. And then we can look at the limiting behavior. So as t goes to infinity, this thing here, X of t, approaches some steady state. And we can see that basically by looking at this equation, taking the limit as t goes to infinity. And we can show that the final state that it approaches is just the time constant tau times the charging power p that we're putting in. Yes, question.
In reality, does P vary with X?
In reality, does the charging power p vary with the state x? I would say
You can charge so much in the first 10 minutes. It takes like wasted amount of time to get from 90 to 95% charge.
yeah. Okay, so the comment is that often if you plug in a phone or something that's super low battery, it'll get from 0 to 50% really quickly, but then 50 to 80 will take as long or maybe longer. And then that last 20% might take a really long time. So part of what's going on there is that smart charging systems try to promote battery health. And charging a battery super duper quickly can sometimes lead to faster degradation. So part of it is that they want to get you to like a useful level of energy quickly. So they allow it to charge at high power, and then they might taper off the charging power over time, basically to avoid degradation. That's part of it. Part of it also is that it gets harder to store the chemical potential energy when the battery is more has higher level of charge. So that's something like the efficiency gets, I guess, lower. It takes more electrical energy to convert to a unit of potential energy as the battery gets fuller. So this model that I wrote down here, this simple model, does not capture that effect, that it might get harder to charge a battery as it's fuller. So this is a simple model of a battery. You can get much, much more complex than this. Yeah. Okay. Right. So there's a limiting state here that you can write down and find the expression for it. And there's kind of an interesting interpretation of the solution to this battery equation in the case where you just hold the charging power constant for a long time. And you can interpret it as a mixture of the initial and the final states. So a mixture, just mathematically, of any two quantities, Z1 and Z2. These could be vectors, could be scalars, could be matrices. We write as just a coefficient lambda times the first one, plus 1 minus lambda times the second one. And here lambda is a weight between 0 and 1. So all this says is if a mixture of Z1 and Z2, you take basically lambda percent. So 40% of Z1, and then the remainder is 60% of Z2. Or it could be 90% over here and 10% over there. So this is just kind of a clean way of writing that. Here, the term, we have an e to the minus t initial that showed up over here, all divided by tau. Okay, so it turns out that that term is always positive, is always between 0 and 1, no matter what the value of t initial or t is, as long as t is bigger than the initial time. So we know it's greater than 0 because e to anything is greater than 0. And we know it's less than 1, basically because this thing goes to 0 when t goes to t initial. So that kind of puts brackets on this. So then we can interpret this thing here as the weight lambda in a mixture. So we have x is basically lambda times x initial plus 1 minus that same term, 1 minus lambda times x final. Okay, so if you want to know kind of what the charge state of a battery is in this simulation where we just charged a constant level for a long time or discharged a constant level for a long time. So at any point along the way, you know that you're a mixture of the initial state and that ultimate state that you'll end up in. And kind of what the weights in the mixture is depends on time. So initially, you're going to start out with 100% weight on the initial state. And then if you let t go to infinity, you'll have a 0% weight over here and 100% weight over here, basically. Okay. So I'm going to go through this one a little bit quickly. We can put numbers on that. Define this thing y, which is basically the percent of the gap between the current state x and the final state here. So this y thing is normalized between 0 and 1. And we can show that y here is just equal to e to the minus delta t divided by tau, the time constant. And so as time progresses here, more and more of the gap basically decays. So when we're at the initial time, 100% of the gap between the initial and the final states is there. And then after one time constant, tau, 37% remains. After two time constants, okay, 14. 3, we're almost all the way there, only 5% left. And 4, only 2%. And here is what that looks like graphically. So we start at the initial time. We're plotting here the state x of t. And we get to so not all the way to the final time, that would be infinity, but we get 5 time constants out. And initially, so after one time constant, we've knocked out about 2/3 of the initial gap. After 2 time constants, about 85%. After 3, about 95%. And after 4, there's only about 2% remaining. So this is just an exponential approach or exponential decay, depending on kind of the direction of charging or discharging. Okay. So the behavior that we get out of these first order linear models is quite simple, I guess is what I'm trying to show. Okay. We have 5 minutes left. I think now is a good stopping point. So let me ask if there are any questions at all in the room or online. So they could be logistical questions about the class, questions about the homework that's coming up, any questions about the material that we covered today. Kind of, it's all fair game. Yes.
For submitting homeworks on Gradescope, do you want the code in any special way, or is just a Python and MATLAB file fine?
Okay, so the question is, when we upload homework to Gradescope, do we want code in any particular format? So let me answer a different question, which is the written portion. So the written portion, I think you can do either on paper or on a tablet, whatever works best for you. If it's on paper, you just take photos of it and upload it from your phone. If it's on, first put it into a PDF bundle and then upload the whole bundle. If it's on tablet, obviously you can just save it as one thing. For the code, I think I will punt this to our TA who will be grading the homework. But I would say, yeah, just like either just screen grabs of your code or else maybe the underlying source file, the MATLAB file or the Python file, I think should be okay. But I will ask our TA basically to answer that question herself in a way that works for her grading. And then we will put out an email to the class with the answer to that. But good question, thank you. Any other questions from the room or online?
I
Yes.
just had a question going back to the previous lecture
Mhm.
about solar with regards to like because basically that would be inside of a load pocket, right? So do they get paid the same capacity factor as somebody who's generating inside of a load pocket, or are they getting paid less because they're
Okay, so we're talking about this slide roughly, right? Okay. So the question is, suppose that we have like a community solar plant. So there's like a vacant field in town and we put some solar panels there. If we sell that power, do we get paid this full clearing price here, or do we get paid something else? Is that the question?
yeah, sort of, because like what I understand for like if I put solar powers on like a rooftop,
Yeah.
or whatever,
Yeah.
I can get paid for the power that I provide to
The utility or the ISO, TSO, right? There's lots of vectors. Yep.
So, but I imagine I'm not getting paid the clearing price. I'm getting paid probably a percentage of what I would pay the utility.
Yeah. Okay. So I guess broadly the question is like, if you produce power kind of out at the edge of the grid and you ship and you don't use it locally, but you ship it back out to the grid, what do you get paid for that power? Okay, so something to note is that wholesale prices are typically about an order of magnitude lower than retail prices. So like what you and I pay for electricity might be around 15 cents per kilowatt hour. But for that same kilowatt hour produced wholesale, it might cost 1 cent or 2 or 3 cents, something like that. So if you're generating at the edge of the grid, really what you would love to get paid would be that retail price, right? The same price that you and I and building operators pay. And if you do get paid that same price, say for a rooftop solar system, that's typically called net metering. And it goes back to old days before digital metering, when you had a physical, like a dial that would just like turn around. Some people still have this, right? The dial would literally spin backwards. So when you're shipping power out, it would just take money off your bill at the same price that you pay, basically. And that policy, you might call it one-to-one net metering, is still active in many places in the US, but not everywhere. And so places like California, where we've seen a lot of rooftop solar actually for like 15 years now, many places in California, actually the whole state, I think at this point has changed that net metering policy. So rather than paying the full retail price for electricity that you produce from solar, they pay a fraction of it. And it's closer to the wholesale price. So now those prices I quoted, 15 cents and 3 cents, are quite different in California, where everything is more expensive. So it might be like 40 cents would be the retail price. And then the wholesale price might be order of 5 or 10 cents, something like that. And so there's a significant reduction in the compensation that people get paid for shipping solar power back out to the grid. And for our purposes, that's kind of interesting because it really puts a strong incentive in place to either use that solar power locally or else store it locally and then use it later so that you can avoid paying the 40 cents a kilowatt hour and not, just only get paid 5 or 10 cents. Yes.
Yeah, a lot of people in the like Central Valley in California where, you have sun 12 hours a day, most of the year, and have rooftop solar, like the grid will basically shut down and say, hey, we can't take any more power. You will have to either shut off your solar panels or pay us to take the
Right.
power
Right.
from you.
Right.
Just because the grid is full.
Right. Yeah, it's an interesting point. So we're kind of at time here, but I'll just try to paraphrase that for folks online. So like in the Central Valley of California, where you have great sun and fairly low demand, not that high population density. And yeah, people, if you need to take off to get somewhere else, please feel free to pack up and go. But in that location where there's a ton of solar on the rooftops, you might have a net flow from a community back out to the grid. Especially at peak sunshine hours at 2 p.m. when demand is fairly low, but solar is producing like crazy. And the utility might say either you're just not allowed to do that. You must shut off your solar, or they might shut it off for you. Or they might stop approving new people who want to put solar on the roof. They might say, sorry, we can't accommodate. We can't host any more solar because we can't tolerate in peak times the power flows from it. Or they might say, sure, you can backfeed power, but you have to actually pay me to put it out onto the grid. So I think an interesting thing here in the merit order is, so if you imagine demand is fairly low and you have like a must-run resource, like a nuclear power plant that it doesn't want to turn off, and actually it would pay to stay attached to the grid rather than to have to shut off and then start up again. So you imagine this block being really long. Then actually you might, so it wants to produce out here, but that's above the demand that's needed. So in that case, the price for electricity can actually go negative if there's just an abundance of supply. And then, yeah, utilities actually have to, yeah, they basically have to pay a lot in that case. So yeah, there are rate plans in places like Texas with a ton of wind where overnight demand is low, wind power is high. Prices actually go negative on the wholesale grid. And there are some kind of utility companies that will pass that negative price on to homeowners and say, if you use power at 2 in, I will pay you for doing that, to basically soak up all that excess. So yeah, things can get weird, especially in renewable dominated markets. And that's
why people put like lithium-ion batteries in the garage and store, medium short-term power.
exactly. So that's a good motivation to put batteries in your garage, for example. Yeah. Okay, so I think we will stop there. Thanks all for your attention. I'll see you on Thursday, and we'll try to catch up and get all the material into your heads that is needed for the homework this week.